Our next speaker is Professor Kendall Lee. Dr. Lee did his PhD at Yale with a really famous neurophysiologist that many of us know, Dr. McCormick, and then trained in neurology and then came to neurosurgery. He's been here at Mayo Clinic for a couple of decades now. I know that probably frightens him a little bit, but I remember meeting Kendall when he first came. So he's going to talk to us about neurochemical closed-loop neuromodulation. Thanks, Kendall.
Which we're all excited about, the 2030 Bold Forward Vision. I'm going to be presenting a lot of work, but we had changed our name from Neuroengineering Laboratories only to Neuroengineering and Precision Surgery. And I'm going to explain this during the second half why the precision surgery is so important. So I think everybody knows this already. More than 200,000 DBS surgeries has happened. Here at Mayo Clinic, I've been fortunate to do about over 2,000 of these operations.
Use a happy one again.
Use a happy one again. Okay.
Why are you smiling?
Why am I smiling?
Yeah.
I felt happy all of a sudden. I don't know. It was just like I was sitting here and all of a sudden I felt happy.
Okay.
Okay. And how about the thoughts of reassurance and the obsession getting in your mind? Are they bothering you or not?
When I feel happy, it doesn't bother me.
It doesn't bother you?
No.
Anxiety is building up or going down or the same?
Going down.
Yeah. So overall,
Pretty not bad.
So what that video is, it's one of the first patients I implanted for obsessive compulsive disorder. And when we stimulate the nucleus accumbens, it was remarkable, where we can actually turn on his laughter. And that's not something that we only discovered here, but others also have found what's called mirth-inducing DBS. But what's interesting about this is that as we now start to stimulate different areas of the brain, we're understanding that we're really playing around with different brain circuits. And so because of that, we have been working on designing these type of technologies called the WINK system, where we're now on third generation of the WINKs. The original one stands for Wireless Instantaneous Neurotransmitter Concentrated Sensor. This one that I'm showing you here is the second generation called WINKs Harmony. And in this one, we added 4-channel stimulation and 4-channel recording. But you know what happened with this at the end? We built the application-specific integrated circuit, spent probably about over $10 million on this. And the ASIC worked for eChem, but it didn't work for ePhys, electrophysiology. So we actually had to go back and start redoing this system. Okay, so few of you in the audience have already seen this. But what you're seeing is a carbon fiber electrode that's been implanted into this male rat. It's in the nucleus accumbens, which is the pleasure center. And we're measuring his dopamine moment to moment. And here's a female rat that's been introduced and comes around and boom, right there. That dopamine spike that you see is, when I first saw this is not my video, but when I first saw this video at Society for Neuroscience, I realized, oh my gosh, what if we can do this in humans? What if we can measure moment-to-moment dopamine, but not only measure it, but control it with the DBS system? And so this is sort of the executive summary, and I'm going to describe to you our latest generation, the third generation of this, that we went back, worked with our division of engineering. And in this device, we set out to perform electrochemistry, so fast scan cyclic voltammetry. And then the middle one, MCSWV, is where we've been able to now use the same recording system to not only measure the relative amounts of dopamine, but the absolute concentration of dopamine. We won one of the first President Obama's Brain Initiative to do that, as well as amperometry, which allows us to measure basically any chemical, even chemicals like glutamate that's non-oxidizable. In addition, we added to it electrophysiology with both local field potential single unit and electrical stimulation. Why do we want to do this? Well, we wanted to do this because the current systems are open loop, meaning that you can stimulate, but there's no way to control it, give it feedback. And so what we're now working on is a closed loop system where we not only are able to stimulate, but from that stimulation, record how much dopamine is being released, and then evaluate and with adaptive artificial intelligence be able to control that stimulation. So with that, just a very quick word of how are we doing this. It's quite simple actually. We use fast scan cyclovoltammetry, which basically uses your oxidation reduction potentials. And in this case, dopamine oxidizes at a very particular 0.6 volts and reduces at about minus 0.2 volts, around there. And that's what you're seeing there in this color plot. Not only that, what we're excited about is that this technique allows us to measure acetylcholine, serotonin. We recently, Dr. Ho-Jin Shin won a very large grant on measuring serotonin as well, which is going to be very important for depression. Dopamine, adenosine, norepinephrine, histamine, hydrogen peroxide, all these other type of chemicals. And we're also using this now with Dr. Max Hawks in the intensive care unit to do point-of-care diagnostics, measuring things like vancomycin, apixaban, those type of things. In addition, we invented a new technique called MCSWV, which uses a combination of voltammetry as well as square wave voltammetry that allows us to measure the absolute level of dopamine. Why is this important? Well, it's important because in the brain, you have phasic changes of that dopamine, but also the tonic changes are just as important. I'm not going to show the calibration curve here, but this has also been expanded to be able to do serotonin recording. I'm not going to play this for sake of time, but this was Dr. Ho-Jin Shin's main PhD thesis. He is now the director, co-director of Neuroengineering and Precision Surgery Laboratories. He published this and covered in Analytical Chemistry. So this is just a summary slide of all the work that Neuroengineering and Precision Surgery Laboratories have done since 2009. First developing just a single channel WINK system, followed by making the MINC system, Mayo Investigational Neural Control System. We connected the two. And then we built the WINK's Harmony, which you see above. And here I'm very proud to introduce to you on the far right the WINK's MAVEN system. So MAVEN stands for Multifunctional Apparatus for Voltammetry, Electrophysiology, and Neuromodulation. And the way that we're envisioning all of this, and we have built this now, is to be able to use this initially in the neurosurgery for deep brain stimulation, measuring these changes, both dopamine and serotonin, as well as we have developed a software system for this that can do all of this in near real time. I don't say in real time because it takes few milliseconds to do all of these type of analysis. In addition to that, we have now been able to use this, and our goal is to treat patients where we can't treat today. Well, one of those is addiction. And what you're seeing here is how we're measuring phasic dopamine changes from cocaine. Cocaine, just let me show you what cocaine is doing when you're doing this kind of recording. This is an animal study, but this is using now WINK's MAVEN technology. And instead of measuring the relative changes, we're now getting the absolute value in this rat in the nucleus accumbens, the pleasure center. And you can see saline does nothing, essentially. But right around 100 minutes, and these are long recordings, we introduce cocaine there, and look what happens to this rat's dopamine system. It just skyrockets, and slowly it comes down. And what was really interesting is this. Now that we have this technique to measure absolute value, it went below baseline. And we believe perhaps it is that falling below baseline that might be critical for the addiction. In addition, we've been using this system to also now stimulate, giving the DBS. And what you're seeing very quickly, this is a lot of slide, but in C, what you're seeing is that before, without DBS, there was that large rise in dopamine, which I just showed you. But now with DBS, we're able to block that effect. The exact mechanism of that, we still don't know, but that is what our lab is currently studying. In addition to that, what you see here is the same thing is happening with cocaine. You can see here, this is a video of the cocaine response. And here's what's so interesting. Now, we are stimulating in the VTA. We actually expected this to raise dopamine, but we were able to modulate it down with VTA, ventral tegmental area stimulation. And then we introduced the cocaine, and it's flat. Now, we're beginning to figure out why all of this might be happening, but we still don't know the exact mechanism. And the oxycodone, similar response as well with the VTA, and that's what this data is showing. Interestingly, what's so dangerous about oxycodone, fentanyl, all of these? Well, these are killing, for example, last year, over 100,000 people overdosed. They overdosed because there's severe respiratory depression. What you're seeing here is that on top, with oxycodone alone, you can see the decrease, the red is showing the decrease in respiration. That's why they die. While we now introduce the same drug with DBS, and there was no respiratory depression. We don't exactly know yet how that's occurring, but we believe that this is a very important finding. And that's the other thing you're seeing here. Now with fentanyl, we're measuring the dopamine, and what you're seeing is the large rise in dopamine, and then it's going to 0, and the reason is because the rat died. In all of our rat experiments, Sarah Vedelson in our laboratory produced these. All the rats that she gave only fentanyl alone, died, while with DBS, none of the rats with DBS died with the same dose of fentanyl. And that's what this is showing. And this is the summary slide showing the respiratory changes related to the DBS effect and fentanyl. I also want to highlight earlier, we spoke about the animal models, the importance of animal models. Dr. Kristen Scheidler in the audience has been working for the past 2 years for her PhD work, development of a large animal pig model of the whole DBS system so that we can take this technology into humans. What you're seeing here is the DBS surgery exactly as we do in humans, except it was done in a large animal, identifying also diffusion tensor imaging, that's the tractography, that we can now do direct targeting of this. And you're seeing here one of the first results that we're now getting in pigs results, demonstrating the large rise in dopamine, the absolute value of dopamine, even in the large model. We're very excited about these results, for which she has won a very large grant. In addition, we have now taken this technology into humans. So let me show you what electrochemical recording. This was one of the very first electrochemical recording we have done in humans. So this is a tremor patient that you can see the video on top left. You can see the tremor. Bottom is the accelerometer. On the left is the voltammetry. You're seeing the color. And right there, you saw the large rise in the signal. And slowly, the patient's tremor went away. But when we analyzed this signal, we didn't know what's stopping these. Is it dopamine? Is it serotonin? Well, it turns out that this signal, and you can see, I'm asking the patient, please hold your hand out. And on the bottom trace, you can see the hand is still. How did that happen? Turns out that this was adenosine. And we know that this is adenosine because the particular chemical fingerprint of adenosine that we have identified. And so our vision is to make an implant that is closed loop, not only being able to record the electrophysiology, which already exists. It's amazing. Medtronic has already released Percept that allows you to do closed loop electrophysiologic feedback. But what our hope is here at Mayo Clinic to develop this system with neurochemical feedback. In addition, what you're seeing is, I want to skip to where the precision surgery part comes in. We have invented a new novel way to do the implant itself with the stereotactic head frame. But this is the device just to show you where we are now going with MAVEN device. We engineered this, and we have now already made the MAVEN system. And this is how we have developed the stereotactic system. I'm going to just very quickly introduce this. I was going to have Dr. Sung come up for this, but I think because of the sake of time, I'll introduce this myself. We have developed a new way of doing the surgery. What you're seeing is X, Y, and Z, the two angle systems here. And we are now able to do these kind of DBS surgery regularly in our operating room. The patents, I'm going to skip the video to get you to this. In the last minute I have remaining, We are hoping now to get rid of the intraop CT. I'm so happy to have found Dr. Sung, who is an expert in AI. And the way that we're doing it is rather than doing CT scan, we're now beginning to do this using 3D surface scan. Why? Because of AI, we're now able to take images like this, which is just a surface scan. You see here, and these are two different types of surface scans, and be able to fuse it with CT scan using artificial intelligence. And it's able to do this kind of fusion in record time. We have already received the IRB and have scanned patients. And what you're seeing on this slide is that we're seeing equal accuracy with 3D surface scan as with CT scan. That's what those numbers indicate. So this is our vision to build all-in-one AI-assisted surgical software to be able to do all of this. Thank you so much.